This webinar will discuss the utility of using NMR liquid relaxation measurements to analyze and to characterize a variety of nanocarbon materials. The data presented here has recently been published in a peer-reviewed journal, Magnetic Resonance in Chemistry. Nanocarbon materials, including carbon nanotubes, graphene, graphene oxide, graphite, and a variety of specialty carbon blacks, are increasingly attracting much attention. They're being investigated because of their stable physicochemical properties, low cost, excellent chemical stability, wide operating temperature range, and long cycle life. They're being considered for use in all types of applications to deliver enhanced performance capabilities to products such as reinforced composites, the development of new generation supercapacitors, sensors, catalyst supports, and electrode materials. However, studying these systems in situ is not straightforward, as the formulations are opaque and are often highly concentrated dispersions in a variety of aqueous and non-aqueous liquids. Further, the physical characterization of all nanoparticulate dispersions poses challenges, especially at high concentrations. Nuclear magnetic resonance, NMR, is a well-known, powerful technique for the analysis of chemical compounds. A high frequency, 400 MHz, is needed for nuclear resolution, and so these types of devices are complex, including the use of liquid nitrogen cooling, and they require sophisticated operation. As such, they are very expensive, and so are found primarily in university and large commercial analytical laboratories. However, only a low field, around 13 MHz, is optimal for dispersion analysis, and see the reference at the bottom by Claves on surface area determination. Because only a small permanent magnet is needed, this means that the device can be made to fit on a laboratory bench. Operation is easy, and such devices are inexpensive, typically compatible in cost with particle sizing instrumentation. They're virtually service-free, and so are ideal for formulation, R&D, and for quality control, quality assurance, and in process laboratories. NMR spectroscopy is one of the most powerful analytical tools used to probe details of molecular structure and dynamics, but it's becoming increasingly apparent that NMR liquid relaxation measurements can provide valuable information about the strength and interaction between a liquid and particle surface functional groups of a material. And we describe these as particulate analysis and molecular analysis. An important feature of the former is the direct measurement of the wetted surface area of suspensions, but the technique also permits observation of influence of morphology and the impact of surface chemistry on wetting and the dispersion of powders in liquids. As such, NMR liquid relaxation complements the classical techniques of particle sizing and zeta potential measurements used to characterize particulate suspensions by providing information that these two latter techniques cannot. In molecular analysis, liquid relaxation can be used to determine not just the absorption of surfactants and polymers onto particle surfaces, but also the interreaction of these moieties with each other. More details can be found in the article published in Spectroscopy Europe. Combining methods of analysis can be extremely useful in all aspects of formulation of suspensions and especially nanoparticulate dispersions. NMR liquid relaxation offers a number of important practical advantages to the formulator. For example, any particle of any size or shape can, in principle, be studied. The dispersing liquid must contain at least one NMR active nucleus, such as the hydrogen atom, proton, and the mixtures of miscible liquids, such as ethanol toluene and cyclohexanone methyl ethyl ketone, can be used. The solid's concentration can be very high indeed. The limit is simply dictated by whether the sample can be transferred into an NMR tube. Importantly, no dilution is necessary, permitting the analysis of samples as they are intended to be used. The measurement time is dependent upon the precision required, but can be very fast, typically between 1 and 5 minutes. From a quality control, quality assurance perspective, the method is also attractive because only a small amount of sample is necessary, around 0.1 of a milliliter. And importantly, the technique is non-invasive and non-destructive. This means that samples can be stored in the NMR tube under, say, ICH, International Conference on Harmonization guidelines, and can be reanalyzed at any later date. So, how does it work? Well, hydrogen atoms in liquids behave a bit like little magnets, shown as blue ellipses. In the absence of an applied magnetic field, the orientation of these proton magnets is random, and so the net magnetic field is 0. When the sample contained in the NMR tube is placed into the cassette assembly of the Acorn Area, it is concentric with an RF coil and is directly within the permanent magnetic field B sub 0, shown by the black discs in the schematics at right and left. The liquid proton magnets, the blue ellipses, align with this permanent magnetic field, a process that occurs rapidly within a few seconds. The XiGo device has patents issued in the US, the EU, China, and Japan. If we apply an RF pulse at an appropriate frequency and duration to the RF coil, a temporary magnetic field B sub 1 is produced, and this is superimposed over the original magnetic field. The proton magnets realign with this new field B sub 1, a process that takes a few microseconds. When the RF pulse is switched off, B sub 1 is removed, and the proton magnets then relax back to their original orientation with B sub 0. A moving magnet in an RF coil produces a decaying voltage, which has an exponential shape, as shown in the graph bottom right. From this exponential decay, we can obtain a characteristic relaxation time for the liquid. Now we define two liquid domains, liquid on the surface of a particle and liquid far away from the particle, the bulk liquid. Liquid molecules on the particle surface, darker blue, relax quickly, on the order of only a millisecond, whereas the liquid molecules far away from the particle, the light blue, relax slowly on the order of a few seconds. Liquid molecules rapidly switch between the surface and bulk domains. It's called fast exchange, and this motion is quicker than the time scale of a single NMR experiment, and that is why we observe a single relaxation time. A suspension of particles in liquid with a large wetted surface area, for example a nanoparticulate pigment, will have a smaller relaxation time than a suspension with a small wetted surface area sample, because there will be more liquid molecules fluid associated with the particle surface. The graph on the left compares the relaxation times for a bulk liquid and surface liquid with that for a suspension, which is a volume weighted average of the two liquid domains. Since the surface relaxation time is so fast, it does not take much surface associated liquid to produce a significant shift in the relaxation time of a suspension. The top graph on the right shows how the relaxation time decreases as the particle concentration increases. The example given is for an aqueous dispersion of 100 nanometer titanium dioxide. Thus, for repeatable measurements, it is important to know the concentration fairly precisely, especially the more dilute a suspension. You can define a new term, the relaxation rate, as the reciprocal of the relaxation time. This change in parameter linearizes the data, the bottom graph at the right, and so provides a much more convenient means to express the data. Relaxation rates in each fluid domain are additive, weighted by the quantity of fluid present in each domain. R sub D is the suspension relaxation rate. PS and PB are the fraction of fluid present on the surface and in the bulk liquid respectively, while R sub S and R sub B represent the relaxation rate of the fluid in each domain, as we mentioned earlier in the previous slide. For those familiar with NMR, we can utilize either the T1 spin lattice or T2 spin echo measurement of relaxation time to determine the average relaxation rate constant. Either T1 relaxation or T2 relaxation can be used. The XiGo Acorn Area device provides both measurements. The T2 measurement is technically more difficult. We use what is called a CPMG, the Karpusel-Maybaum-Gill pulse sequence, but it is faster than T1. We use either an inversion recovery or a progressive saturation method. While both T1 and T2 are shifted by the presence of the particle surface, the magnitude of the shift may be significantly different. Each approach has advantages and disadvantages. Part of method development is to decide which relaxation time, T1 or T2, is more appropriate for a given application. In contrast to measurement of particle size by dynamic light scattering or light diffraction, where the raw scattered diffractive intensity data has to be deconvoluted by means of complex algorithms, sums of exponentials or sums of Bessel functions, the relation between NMR relaxation and wetted surface area is surprisingly simple. Conversion of relaxation time to surface area is a straightforward calculation. As in the BET gas adsorption method, monolayer coverage of fluid onto the particle surface is assumed. The specific surface relaxivity constant, Ka, clearly depends on both the particle type and dispersing liquid. For a given interface, K sub A must be determined experimentally with reference to another analytical technique. However, for a given particle-liquid combination, when monitoring relative changes in particle surface area, for example in milling, the differences in relaxation time are absolute, and so determination of a specific value for K sub A is not necessary. No assumptions are made about particle size or distribution or shape. For non-porous materials, a single exponential fit can be made to the relaxation data, and the example shown is for a 20% aqueous dispersion of a polyurethane latex. But now, let's look at some results for nanocarbon materials. The application performance of carbon black is determined by its nature, including how it is manufactured, and level of dispersion achieved. The particle size exerts the greatest influence on color. The finer the size, the darker will be the color. All carbon blacks contain aggregates that impact the surface area. A high surface area is associated with greater blackness and better, more uniform coating. Hence, aggregation needs to be kept to a minimum. The application performance of a carbon black is determined by its nature, including how it was manufactured and the level of dispersion achieved in formulation. The most important physical properties include particle size and wetted surface area. The particle size exerts the greatest influence on color. The finer the size, the darker the color. All carbon black contain aggregates and agglomerates that impact the total wetted surface area. Because high surface area is also associated with greater blackness, aggregation needs to be kept to a minimum, and any analytical technique that can provide an indication of the degree of aggregation is most welcome. The level of dispersion in any given formulation is, of course, strongly influenced by the mixing equipment and procedures used. As we've already noted at the beginning of this webinar, owing to the opacity and high concentrations normally used, precise, accurate physical characterization of nanocarbon dispersions is often difficult. Here we show a series of nanocarbons of varying primary particle size as assessed by transmission electroscope microscopy. These nanocarbons are used in the highest quality automotive coatings. We compare the surface area calculated from the primary size with that determined for a well-dispersed 5% suspension in tetrahydrofuran. In each case, the dispersion has a lower wetted surface area owing to the presence of aggregates. As we can see, the ratio of the two surface area values increases as the primary particle size increases, likely reflecting a larger concentration of aggregates. The 220 nanometer nanocarbon material samples are two different batches that were subjected to different dispersion processes. Nitrogen BET adsorption is currently used as a QC tool to determine surface area, but it can be tedious and time-consuming. Critically, it is only applicable to the dry powder material and cannot provide any information about what happens when the powder is dispersed. By contrast, NMR relaxation is simple and quick and works with almost any solids concentration in virtually any liquid. Well, let's look at some graphene oxide. Graphene oxide sheets are readily obtained in large quantities from graphite. Moreover, the oxygen groups on the carbon backbone of the sheets make the sheets partially hydrophilic so that they absorb to a water surface, creating an extremely strong, flexible interfacial structure. Thanks to the mechanical integrity, it is possible to transfer large-scale films from the water surface directly onto suitable substrates. Chemical reduction to graphene then results in transparent conductive films. The ability to distinguish between molecules at the graphene oxide interface and those in the bulk is invaluable in obtaining information on the interfacial interactions and structure of graphene oxide materials at any relevant preparatory concentration. Two samples here were supplied by Miss Imperiali, University of Leuven. They were very dilute, but sample 1 was much more concentrated than sample 2 and illustrates the impact of dilution. We determined the actual concentration by evaporation to dryness. From the material preparation, each graphene oxide would have different degrees of oxidation, and this was not known at the time of our measurement. It is clear that the single exponential fit, the blue line, to the data, the red dots, is good for both samples. Reproducibility of data was quite acceptable, coefficient of variation of less than 2% for each sample. The data shows a significant difference in wetted surface area between the two dispersions. Sample 1 had a larger wetted surface area compared with that for sample 2, 1,326 compared with 786 square meters per gram respectively. The wetted surface area values obtained from the T2 relaxation data are similar in magnitude to BET literature data for graphene oxide. Let's look at some nanographites. It has been suggested that graphene could entirely substitute carbon fiber, for example, aerospace and defense applications, thanks to its higher strength and lightness. Single and multiple graphene layers can be produced as dispersions in a variety of liquids. The ability to monitor milling and comminution processes in almost real time on opaque samples and without dilution provides a major practical advantage for NMR relaxation over other particle characterization techniques, especially particle sizing by light scattering methods. The example shown in this slide contains 3 data sets. The first set, S0 to S10, are 2 weight percent aqueous dispersions that were prepared by small bench scale milling in the laboratory of dry nanographite powder at a constant mechanical energy, with increasing addition of a polymeric surfactant dispersant. It is clear that the S10 sample has been overdosed. The smaller wetted surface area is likely a result of aggregation through depletion flocculation. Overdosing with surfactant impacts both the performance of the final product and also the economics of the process. A fast and simple analytical tool to determine that this is the case is highly advantageous in both method development and in quality control. The SP sample was the same as sample S0, except the dispersion was prepared at 20 weight percent using pre-production size equipment. The second set of samples, EO1, EO2, were made from a different batch of dry nanographite and are dispersed in ethanol, again at 2% weight. EO1 and EO2 were initially processed in 2 different ways in an attempt to reduce the amount of particle agglomeration that had been observed previously. These data show us that the different preparation methods used with E1 and E2 do indeed lead to differences in the total wetted surface area, And it is important to note that since the surface chemistry is assumed to be the same, we would be able to see the effect of the change in milling techniques even without having measured the relaxivity constant for this interface. The final set, CP01, was a single sample dispersed again at 2% in cyclopentanone. This sample was highly aggregated, and attempts in our laboratory to redisperse using a microhomogenizer were unsuccessful. So it is not surprising that the wetted surface area was extremely small, less than 10 square meters per gram. For porous solids, there are additional considerations. In this case, the total NMR signal is now proportional to the signals from both the total internal pore volume, the external volume of liquid on the material surface, and the external volume of bulk liquid. Hence, the measured NMR relaxation time can differ depending upon the prevalent pore size and shape. The equation is a double exponential decay as illustrated in the upper schematic. The example shown is a 10 weight% aqueous suspension of a 1 micron porous silica. Note the pore fit, the blue curve, at high magnetization with the experimental data, red dots. This deviation is typical of materials that possess porosity. In such situations, a double exponential fit can be used, as illustrated in the next slide. Porous graphene materials, including graphene nanomesh, crumpled graphene, and graphene foam, have attracted tremendous attention and research interest, owing to their exceptional porous structure, which is high surface area, high pore volume, in combination with the inherent properties of graphene. Achieving complete wetting of porous materials, though, can be challenging. NMR liquid relaxation measurements characterize any fraction of a particle surface that is wet by a liquid, and so can be used to optimize the choice of wetting liquid or liquids. Here we show T2 relaxation data for 2.8% samples of the same porous graphene dispersed in water and ethanol, respectively. The overall reproducibility was excellent. The coefficient of variance was less than 1%. Note the poor theoretical single exponential fit to the raw data, particularly at high magnetization. The estimated surface area values calculated using the T2 times are virtually the same, but this is an erroneous conclusion. The next slide shows the same data but fitted to a double exponential. Now, note the much better fit, the green dots. From this we can extract two sets of data. The short T2 value was used to determine the total available surface area. The water dispersion has a much longer decay and a 20% longer short decay, indicating that a much more mobile layer of water altogether exists at the graphene surface. The data suggests a stronger interaction with ethanol. The T values for ethanol are much less than that for water, and this implies better wetting, as might be expected. In conclusion, I hope that in this brief time allotted to me that I've persuaded you that NMR relaxation is a new and very powerful tool that can be used to study and optimize formulations of nanocarbon materials by providing information that cannot readily be obtained with other characterization techniques. A major advantage is to be able to make measurements using industrially relevant concentrations. Further, the technique is non-destructive, so samples can be stored and measured at any future time, permitting later reanalysis of reference samples. Long-term aging studies can be undertaken quite trivially. Thank you. If you would like to see the Acorn area, or if you need further information or would like to discuss how NMR relaxation measurements might help you in your application, please contact me at www.XiGo Nanotools.com.